Imagine building the invisible backbone of the apps you use every single day. The complex systems that make everything from tracking your morning run to getting groceries delivered kind of magically work. How do these tech giants actually make it all happen, handling like millions of users and transactions without breaking a sweat?
It's truly fascinating when you think about it, isn't it? These aren't just apps, they're incredibly intricate digital ecosystems. And today we're embarking on uh, a really fascinating deep dive into the architecture of four distinct large-scale systems.
That's right. Our mission today is to unpack the blueprints for, well, a fitness tracking app, a massive distributed cache, a rapid local delivery service, and a high-frequency trading platform. We're going to explore their core challenges, some ingenious solutions, and, the fundamental principles that keep them running smoothly at just immense scale.
You're definitely in for an illuminating journey because we've gathered insights from expert sources, really, the minds behind these types of systems. We'll
Yeah.
take you chapter by chapter through each design, dissecting the requirements, the foundational components, and all those clever deep dives that address the real-world challenges.
Yeah, this is basically your shortcut to being truly well-informed, to
Yeah.
understanding the engineering brilliance that powers modern digital life. So buckle up because we're about to dive deep. Okay, let's unpack this first one. We're kicking off our deep dive by exploring Strava. It's that incredibly popular fitness tracking application. You probably know it, maybe even love it. Users record and share activities, mostly running and cycling, right? With their networks, getting detailed analytics on performance routes. For this deep dive, we're going to zero in on the core system design challenges just for these specific activities. We're focusing entirely on Strava first before we move on. Hashtag tag 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 one, function requirements.
Right. So to begin any system design, you first need to understand precisely what the system must do, from the user's perspective. These are the core functional requirements. And for Strava, they clearly define the essential interactions we absolutely need to support.
I understand. So first up, users absolutely need to be able to start, pause, stop, and crucially save their runs and rides. This is like the most fundamental interaction, isn't it? The very first thing a user does to track an activity,
Yeah.
and then how they finish it. It's managing that whole life cycle.
Precisely. Then, once an activity is actually in progress, the second core requirement is that users should be able to view their activity data.
Yeah.
Things like their route unfolding on a map, the distance they've covered, the elapsed time. This real-time feedback is just crucial for athletes. It lets them monitor performance, right there on their device while they're still moving.
Yeah, I can't imagine a fitness app without that. It's essential. And then once activities are completed, users naturally want to review their performance, right? So they should be able to view details about their own completed activities. That's kind of a given.
Mm-hmm.
But, and this is huge for Strava's social feel, users also need to be able to see the activities of their friends. That really fosters the community aspect, the friendly competition. That's a big part of the platform's value.
Indeed, yeah. That social sharing element is what truly differentiates it from just a simple personal tracker. Now, it's equally important in any system design like this to explicitly define what's below the line or, out of scope for this particular problem. For instance, while Strava definitely has extensive social features, we're not focusing on the mechanics of adding or deleting friends. That's friend management. And it introduces a whole different set of complexities we don't need right now.
Makes sense. And we're also not touching authentication and authorization. So logging in, signing up, verifying who the user is, managing permissions. We're basically assuming that crucial part is handled by some separate dedicated service. That lets us concentrate purely on the core activity tracking, right?
Exactly. And we're also explicitly leaving out things like commenting on or liking runs. While these are definitely key social features on Strava, they bring in distinct design challenges. Think about real-time interactions, notification systems that would distract from our primary focus here, which is the core mechanics of tracking and viewing activities. By narrowing the scope like this, we can really concentrate our design efforts on the most critical parts for this exercise. Hashtag tag 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 2, non-functional requirements.
Okay, so once we have a clear picture of what the system needs to do, we then need to define how well it needs to perform those functions. These are the non-functional requirements. And for a large-scale system like Strava, they really guide our architectural choices, often dictating the technologies, the patterns we'll use.
You're absolutely right. They're the quality attributes. For Strava, a paramount non-functional requirement is that the system should be highly available. This means it just has to stay operational, accessible to users as much as possible, even if parts of the system have issues. For a fitness app, this usually implies availability, often takes precedence over strict, immediate consistency in many cases. Think about it. If someone can't upload their run, That's a major problem, right? It impacts their main use case. But a slight momentary delay in seeing a friend's new activity, that's generally less critical, probably more acceptable.
That's a really crucial trade-off, isn't it? And thinking about where people use Strava, often outdoors, on trails, roads where connectivity can be, well, patchy, it's imperative that the app must function reliably even in remote areas without network connectivity.
Mm.
This immediately points us towards certain design choices, especially for the client app, doesn't it? To make sure it doesn't just die when the network drops.
It absolutely does. And kind of hand in hand with that, the app needs to provide the athlete with accurate and up-to-date local statistics during the run or ride. This ensures the user gets immediate feedback on their performance, current pace, distance, time, without needing a constant real-time server connection. That on-device processing is vital for a responsive, reliable experience.
Totally. And finally, to really be a platform like Strava, the system has to scale significantly. Specifically, it should scale to support a massive number of users doing things at the same time, up to 10 million concurrent activities. That's a huge number of users actively recording, interacting with data simultaneously. That's going to heavily impact how we design the backend for data handling and processing.
That's a truly demanding scale, yeah.
Right.
It pushes us towards distributed solutions almost immediately.
Hmm.
Now, as for what's below the line for non-functional requirements here, we're deliberately not getting into compliance with complex data privacy regulations like GDPR or CCPA. Those are intricate legal and technical areas, critical for a real company, obviously, that they divert our focus from the core system architecture for this exercise.
Right. Nor are we tackling advanced security measures beyond, basic authentication. Things like protecting against sophisticated attacks or ensuring data integrity at every single layer. We're focusing purely on the core operational stuff, delivering the main features at scale rather than the broader security posture or legal compliance. Hashtag 3, capacity estimation.
Okay, now let's try and put some concrete numbers to these requirements. Capacity estimation as well, it's an absolutely critical step. It gives us a clearer understanding of the sheer scale of the infrastructure we're going to need. Helps visualize the volume of data, the number of requests for a service as big as Strava.
Right, so let's break down the annual data storage first. If we estimate maybe 100 million daily active users, and let's assume each one does an activity each day, that translates to roughly 100 million new activities being recorded daily.
Wow.
Over a full year, that's about 36.5 billion activities. That's just an astonishing number of runs and rides.
It truly is. But let's dissect the storage cost per activity to really understand the impact. Basic metadata for each activity, stuff like status, user ID, start time, end time, it's incredibly lightweight. We can estimate maybe around 100 bytes per activity. That's minimal, not our primary storage worry.
But the route data, that's where the bulk of the storage cost comes in, isn't it?
Yeah.
Those GPS tracks are continuous streams of data. So if we figure an average activity is, say, 30 minutes long, and we capture GPS coordinates pretty often, like every 3 seconds, that results in about 600 individual points recorded per activity.
Correct. And each of those route points needs 3 crucial pieces of info. Latitude, 8 bytes, longitude, also 8 bytes, and a precise timestamp, another 8 bytes. So for each point, that's 24 bytes total. Multiply that 24 bytes by the 600 points we estimated per activity, and you arrive at roughly 15 kb per activity just for the route data alone. That's way more substantial than the metadata.
Okay, so 15 kb per activity, mostly for those GPS traces. Now, for the grand total, we take that 15 kb per activity, multiply it by those staggering 36.5 billion activities annually. That calculation comes out to an immense 547.5 terabytes of new data being generated and stored every single year.
And this is where the interesting discussion happens. On the surface, 547.5 terabytes per year sounds absolutely massive, right? Maybe overwhelming. However, in the context of modern large-scale distributed systems, this is large, but crucially, it's a manageable amount of data. It's not trivial, sure, but it also doesn't immediately scream petabytes of real-time, highly transactional data that would demand the most extreme storage measures. Technologies available today, cloud storage, distributed databases, they're well equipped to handle this scale. So this estimate tells us, yes, we need robust storage, but we're not dealing with an insurmountable volume that breaks established patterns, sets realistic expectations. Hashtag 4. Core entities.
Okay, requirements down, scale estimating. Let's talk about the fundamental nouns of our system, the core entities. The purpose here isn't to get bogged down in every specific database column just yet, right? It's more about defining the main information units our system manages. Gives us a solid foundation for the API later.
Exactly. It's about identifying the most important categories of information, the main building blocks. Firstly, and pretty straightforwardly, we have the user entity. This represents a person using the app. It would logically hold profile info, settings relevant to their Strava experience.
Then, absolutely central to Strava, we have the activity entity. This is an individual run or ride. It would include vital details, type, run ride, start time, end time, the crucial route data that stream of GPS coordinates, plus total distance overall duration. This entity is really the heart of what Strava tracks.
And speaking of that route data, we have a bit of a design choice here. We could treat route as its own distinct entity, basically a dedicated collection of GPS coordinates for an activity. Or maybe simpler for many cases, it could just be a complex data field directly embedded within the activity entity itself. This kind of flexibility early on is good, lets us defer precise decisions until we see access patterns.
And finally, even though friend management, adding deleting friends is out of scope for this specific deep dive, we still need the concept of a friend. This entity conceptually represents that connection, the friendship between two users. This relationship is absolutely necessary to support activity sharing, which is a core functional requirement. Without it, viewing friends' runs just isn't possible.
Exactly. These core entities, maybe simple and abstract at first glance, they really define the fundamental boundaries of what our system needs to track and manage. They serve as the bedrock, the foundation upon which our API will be built, and then the whole system architecture. They're like the scaffolding for our data model. #5 API or system interface.
All right, core entities defined. Let's think about how the mobile app, the user's main interface, talks to our backend services. This is where we define the API, the system interface. The goal is to directly map these API endpoints to the core functional requirements we set earlier, ensuring every user action has a clear path to the server.
That's right. It's formalizing the interaction. The first, most foundational call is starting a new activity. For this, we need an endpoint to create a new activity, typically a pxActivities endpoint. The client sends a simple request body specifying the type, either run or ride. The server, on success, returns the new activity object, including its unique ID, back to the client.
Then users need to pause, resume, eventually complete activities. For managing this lifecycle, we need an endpoint to update the state of an activity. A common pattern for partial updates is patchactivities.activityID, right? The request body includes the new state, like started, paused, or complete.
Precisely. And a quick but important note here on patch versus PT. Patch is generally better when you only update a subset of fields. It's more efficient, less data over the network, less server processing. PT, on the other hand, usually implies replacing the entire resource. While in interviews, they're sometimes treated the same for simplicity, showing the nuance of patchy efficiency is good.
Absolutely. Shows good granular API design sense. Then, while an activity is happening, we need to add new location data continuously. So an endpoint to add a new location to the activities route. This would probably also be a POS, maybe postactivities.activityIdroutes. The client sends the single new location as a GPS coordinate object, handles that streaming GPS data.
And finally, for viewing activities, we need two distinct endpoints here. First, to get a list of activities for a user, either their own or their friends. We can use a get activities. It takes query parameters like mode, user, or friends, and page size for pagination. It would return a partial list of activity objects, meaning just a subset of fields like ID, type, distance, start time, limits network data for a quick overview.
Right, you don't need every single GPS point for a list view, just the basics. Then, when a user taps a specific activity from that list, they want all the details, the map. So to get an activity by ID, full details, we'll have bitactivities.activityID. This returns the complete activity object with all its data. These well-defined APIs really lay the essential groundwork for our high-level system design. #6, high-level design.
Now we move into the high-level design phase. We start piecing together the components, the flows, showing how our functional requirements can actually be met. The strategy here is always start simple. Build the simplest possible system that meets the core functionalities first. Then and only then do we iterate, add complexity to handle the non-functional requirements during our deep dives. Build that solid foundation first, step by step.
If pragmatic evolution makes sense.
Yeah.
So let's tackle requirement 1. Users should be able to start, pause, stop, and save their runs and rides. How does the most basic system handle this?
For this initial requirement, we can sketch out a very basic client-server setup. We have the client app, the mobile app. It talks to an activity service on our backend, and that service uses a database to store activity info. Simple 3 tiers.
Okay, so user opens the app, hits start activity. What happens in this basic flow?
Client makes a POC Act activities request to the activity service, specifying run ride. Activity service creates a new entry in the database, gets back an ID, and returns the activity object with the ID to the client. That ID is key for later updates.
And if they pause or resume mid-activity?
Client sends a patch activities.activity ID to the activity service with the updated state. Paused or started. Activity service just updates the database record. When the activity is truly over, user hits save activity, another patch request goes to the same endpoint, this time with state. Complete, finalizes it.
That seems straightforward for state changes. But there's a subtle detail. Accurately handling the total activity time when a user pauses multiple times. Just tracking a start timestamp and subtracting from end timestamp won't work right. Pauses mess that up. The time would keep ticking incorrectly.
That's a very common, and important pitfall. The robust solution isn't simple start-end times. Instead, you maintain time via a detailed log of status updates and timestamp pairs. Like, you'd record status that started, timestamp 0000.0000 status, resumed, timestamp 0.15.0000 status, resumed, timestamp 00.15000000 the status, stopped, timestamp 0.2500. When stop activity is hit or it's finalized, you calculate the total elapsed active time by summing durations between these pairs, but crucially excluding pause periods. So in that example, it's 10 minutes start to pause plus 5 minutes resuming to stop, 15 minutes active time. This method is really clean, provides accurate data, and naturally allows for future features like showing pause times or total time versus active time.
That's quite clever. Adds a bit more back-end complexity, but gives much better data. Okay, requirement 2. While running or cycling, users should be able to view activity data, including route, distance, and time. The core here is accurately tracking distance and route by recording GPS coordinates constantly, assuming modern phone GPS is reliable enough.
Absolutely. The client app is central here. It uses the phone's built-in location services, iOS core location, Android's Google Location Services API to get GPS coordinates. Frequency can vary, maybe 2 seconds for a bike, 5 for a run. Once a new coordinate is captured, the client app sends it to our POC activities.activity iDroutes endpoint.
So the server gets these frequent updates. What does the backend activity service do?
Backend activity service receives the new coordinate, updates the route table, or the route field in the activity entity in the database with the new coordinate and timestamp. Crucially, it also updates the distance field for the activity. It calculates the distance between the new coordinate and the previous one using something called the Haversine formula. That formula accounts for the Earth's curvature, which is important for accuracy over distance. The sum of these small segment distances gives the total distance covered.
A quick note here, though. Our initial design sends these location updates to the server as they happen. But sharp listeners might be thinking, couldn't a lot of this be handled locally on the client? Save bandwidth, improve resilience. You're totally right to think that. That optimization, which really reshapes the system, is usually a deep dive topic. Candidates often overlook it initially. We'll definitely explore that powerful idea soon.
Indeed. Finally, requirement 3. Users should be able to view details about their own completed activities as well as the activities of their friends. Once activities are done, marked complete, their data is already stored in our database.
So getting this data is fairly straightforward. Query the database for state complete. Filter based on the mode parameter, user ID, user EE for the user's own stuff, or user in select friended from friends, where user ID for friends activities. Apply standard pagination with limit and offset. Yep. And for efficient friend lookups, especially at scale, our friends table needs user ID and friended columns. Importantly, relationships should be bidirectional, 2 entries per friendship, A, B, and BA. Primary key on the first column, user ID, makes finding all friends for a user fast. And the viewing flow is usually 2 steps, right? Initial GET activities gets a basic list, ID, type, distance, keeps the load fast. Then, user taps an activity, triggers a second GET activities, that activity ID request for the full details. And to show the route map, you use that array of coordinates with something like the Google Maps API to draw the path. This simple layered approach covers our basic functional needs. #7. Deep dives. Okay, now the really exciting part, the deep dives. We have our basic working Strava system, but it's not quite ready for the real world for true scale. These deep dives are where we tackle the non-functional requirements, crucial optimizations, scalability challenges, pushing our design from just functional to properly robust and performant.
Our first deep dive hits a critical real-world scenario from the non-functionals. How can we support tracking activities while offline? So many athletes exercise in remote spots, trails, or just areas with bad connectivity. They still need accurate tracking, right? Without interruption.
This brings us to a really transformative realization, doesn't it? It often separates good designs from great ones. Recognizing the power of the client, the phone, as a mini server, or maybe more accurately, a powerful edge device. The first instinct might be to stream every single GPS point straight to the server as it happens. But then you hit a dead zone on your run and puff, your data is lost, or your battery just drains from constant network pings. Terrible user experience, and really inefficient for our servers too. The key insight, as you mentioned, is that for non-real-time sharing, we can fundamentally shift the burden of tracking to the user's device. It's not just optimizing, it's strategically using edge computing, leveraging the phone's sensors, processing power, local storage.
Exactly. This gives several immediate huge benefits. First, paramount. Activities track reliably, continuously, regardless of network. Your run data is safe if the signal drops. Second, huge savings on network bandwidth. No constant pings every few seconds. Data is sent once, maybe when complete or pause saved or connection returns. And third, showing accurate, up-to-date local stats becomes effortless, instant. All calculations happen right there on the device, no network latency. Massively improves perceived responsiveness, reliability.
So how does this actually work in practice? What's the mechanism on the device?
Okay, so the phone's location services record GPS coordinates constantly, say every 2 to 5 seconds. This raw event data gets stored locally, initially in an efficient in-memory buffer, basically an array of coordinate timestamp pairs. To prevent data loss if the device crashes, app closes, battery dies, this in-memory buffer is periodically persisted to the device's local storage, maybe every 10-15 seconds. On iOS, you might use core data or user defaults. Android, maybe room or shared preferences.
And if the app closes unexpectedly or the user resumes later?
If the app reopens or an activity resumes, it first checks that local storage, loads any saved data back into the buffer, and tracking continues seamlessly. Once the activity is fully complete and the device is back online with a stable connection, all that accumulated data gets sent to the server in a single big request. For really long activities, you might need chunking strategies to break that single request into smaller parts. Plus, for even better durability, you could implement a background sync mechanism. Tries to upload data periodically whenever a connection is available, even if the activity isn't complete. Saves incremental progress. Only when the server confirms successful receipt and persistence is the local buffer finally deleted. The main trade-off here is balancing GPS tracking and persistence frequency against battery life. For really large data sets, maybe a local SpyLite database is better than simple key-value stores. This deep dive really shows how offloading that high-frequency write load to the client simplifies the backend significantly. It can remain a more manageable client-server architecture without needing complex microservices right away.
That's a huge optimization. Yeah, fundamentally changes the backend's workload.
Which leads nicely to deep dive 2. How can we scale to support 10 million concurrent activities? End board. The offline tracking we just discussed already cuts backend requests dramatically, maybe 100x or more, since data is sent once at the end, not streamed constantly.
Even with that huge reduction, we still need to think about bottlenecks, especially our central database, which will eventually hold massive amounts of activity data. Our earlier estimate was around 547.5 terabytes of new data annually. Large, yes, but as we said, manageable with modern infrastructure.
So how do we handle this vast but manageable volume in the database to keep performance good? The most fundamental strategy for large data volumes and scaling writes reads is sharding. We split the data across multiple database instances or clusters. A really effective sharding key for Strava would be the activity completion time, or maybe time-based range partitioning. Why? Because most user queries, social feeds, they're typically for recent activities. By partitioning by time, we keep hot recent data on faster, more active shards and cold, older data on separate, less accessed shards.
And building on that time-based idea, you mentioned data tiering.
Exactly. We introduced data tiering to further optimize storage costs and performance. Older data, say activities from years ago, are accessed way less often than today's runs, so implement a lifecycle policy. Hot data, maybe last 30 days, lives in fast, expensive storage, high-performance SSDs on the primary cluster. Warm data, say 312 months old, moves to slower, cheaper storage. Cold data, 1 year, migrates to archival, super cost-effective object storage like S3 or Google Cloud Storage. Retrieval is slower there, but costs are minimal. Drastically cuts operational costs for historical data without hurting active query performance.
What about back-end caching for this kind of system?
Caching could be introduced on the back end, sure, if we found ourselves frequently querying the exact same completed activities or maybe highly aggregated summaries. Reduces read load on the DB. However, given users usually view unique individual activities or personalized feeds, and our read throughput for individual activities isn't expected to be astronomical, thanks to client processing, it might not be the highest priority for an initial back-end cache on individual activity reads, but it's always an option if load times for popular activities become an issue. As for the database choice itself, honestly, most popular relational databases like Postgres or MySQL would work really well. The volume is manageable, no crazy read-write throughput per record, forcing us into specialized NoSQL right away. A well-sharded relational DB offers plenty of headroom.
And for the activity service, the application layer. Given the relatively low read-write throughput per activity due to client-side optimization, you don't necessarily need complex microservices immediately. You can just scale that single activity service horizontally, add more instances when memory, CPU, or network limits are hit. Pragmatic, cost-effective growth management.
That's the beauty of starting simple, scaling as needed. Okay, Deep Dive 3. How can we support real-time sharing of activities with friends? This is where friends can watch you mid-run ride, seeing stats and route update in near real time. Adds that live, interactive social layer.
This definitely pushes the design towards more dynamic real-time systems like live comments or chat apps. To do this, we'd need to reintroduce periodic server updates during activities, right? So while the local device still handles the athlete's immediate display, those location updates and stats now also get sent to the server every, say, 5 seconds, in addition to the final sync.
And as the server gets these real-time updates from the active athlete, the activity service persists them in the DB, like before. But crucially, it then immediately broadcasts these updates to all of that user's friends who are currently viewing or subscribed to their live activity. Now, your first thought might be WebSockets. And technically, you could use WebSockets or server-sent events, SSE, for persistent connections.
But you'd argue that might be over-engineering for this specific problem. Why? Why not jump straight to WebSockets for real-time?
Because there are two key insights here that often suggest a simpler, more effective, maybe even more scalable polling mechanism is actually better. First, unlike chat where messages arrive unpredictably, these updates are highly predictable. The next one should come in 2 to 5 seconds. This predictability allows for very efficient timed polling intervals from the friend's clients. Second, and maybe more importantly, absolute, millisecond-level real-time precision isn't critical here. A slight delay of a few seconds is perfectly acceptable. It doesn't ruin the experience of watching a friend's progress. It's near real-time, not sub-millisecond trading data. So a simple polling mechanism. Friends' clients periodically ask for updates, maybe at the same interval the athlete sends them, offset slightly for latency that would work without the overhead of managing millions of open WebSocket connections.
Exactly. A well-tuned, simple polling strategy often scales better and is easier to implement for this kind of predictable, near real-time data. And to further enhance the user experience for the viewing friends, we can implement a smart buffering system on their client side. Intentionally lag the displayed location data by 1 or 2 update intervals, say 5–10 seconds. This buffering creates a much smoother, more continuous animation of movement on map, eliminates jarring jumps or erratic movements you might get with pure, unbuffered updates due to network jitter. The athlete appears to move fluidly, providing a much more engaging, live stream-like experience. It's a calculated trade-off. Sacrifice absolute millisecond accuracy for significantly better visual experience. Plus, it naturally compensates for network latency and minor server delays. Consistent viewing experience. That's a great example of a subtle but impactful trade-off for a better UX.
Yeah.
Okay, fourth and final deep dive for Strava. How can we expose a leaderboard of top athletes? Feature allowing users to see rankings by activity type, distance, filterable by country, region, city, showcasing that competitive aspect.
The most straightforward approach, the naive database query, would be to just select usernames, assume distances from the activities table, join with users, group by user ID, order by total distance descending. A SQL query might look like, select u.name, SEMAA distance from activities a join, u on a.userid equal u.userid, where a state equals complete, and a dot type equals run group by user id order by total distance DSC.
But that sounds like a recipe for disaster when you have hundreds of millions of activities to aggregate on every single request.
It is, absolutely. The challenges are immediate, incredibly slow, aggregating maybe billions of records per request, super high latency for the user, places immense repetitive load on the primary database. Plus, doesn't handle dynamic ranking changes well. It just doesn't scale for real-time leaderboards.
So what's the next step up, acknowledging those performance issues?
Next approach, periodic aggregation. Instead of calculating on demand, create a separate Dedicated leaderboard table storing pre-calculated aggregates. A background job runs at regular intervals daily, hourly, every 15 minutes, depends on freshness needs, updating these aggregates based on new activities completed since the last run. This transforms the leaderboard query into a simple, highly efficient select from the pre-aggregated table, drastically cuts read latency and DB load.
That's definitely faster for reads, but it immediately screams eventual consistency. Your latest run might not show up instantly.
Precisely. The challenges are indeed that it's not real time. This eventual consistency can confuse users if their latest activity isn't reflected immediately. Less satisfying. Plus, finding the optimal update frequency is tricky. Too frequent. Strain background processing and DB. Too infrequent. Data gets stale, less valuable for competitive users. It's a compromise.
And for a truly scalable, real-time, high-performance solution, especially for a competitive platform like Strava.
For that, we leverage Redis sorted sets. This is a highly efficient, in-memory data structure, perfect for managing ordered lists with associated scores ideal for leaderboards. We'd use Redis sorted sets, user IDs as members, cumulative total distances or other metrics as scores. When a new activity is logged and completed, we simply increment the user score in the relevant sorted set. Querying the leaderboard becomes a highly efficient operation. Retrieve the top N members from the sorted set. Redis does this in logarithmic time, even with millions of entries.
How do you handle filtering by country or specific time ranges with this Redis approach? Those were part of the requirements.
For country filtering, straightforward approach. Create separate sorted sets per country, e.g. leaderboard.run.usa, leaderboard.run.uk, etc. When an activity logs, update both the global and the relevant country-specific set. Querying uses the appropriate country set, still highly efficient. For time range filtering, last 24 hours, current month, it gets more sophisticated. Requires combining Redis sorted sets and Redis hashes.
Interesting. How did that work for time ranges?
Okay, we store two things for each activity in Redis. First, a sorted set entry. Activity ID as member, timestamp as score, maybe in a set called activities.timestamps. Lets us query activities by time quickly. Second, a hash entry for each activity ID, key activity.activity.id, field store user ID and distance for that specific activity. When a query for a time range comes in, for example, the last 24 hours, we first use range by score on activities.timestamps to efficiently get all activity IDs within that time window, super fast list retrieval. Then, for each of those activity IDs, retrieve the corresponding user ID and distance from the individual hash entries. Finally, aggregate these distances by user ID in memory, summing them up for the period. Sort these aggregated results for the final leaderboard. Allows dynamic time window queries without pre-calculating every permutation.
That's quite a few steps to generate the result. What are the main challenges with this sophisticated Redis approach? Consistency, memory.
Primary challenge. Data consistency between Redis, real-time leaderboard, and our primary relational database, source of truth. Need robust failure rate tree handling for Redis updates. If DB write succeeds but Redis update fails, leaderboard is stale. Requires robust messaging queues, retry mechanisms. Also, Redis is in memory, so memory limitations. Storing complete leaderboard data for all possible combinations, activity types, time ranges, geo-filters, especially with all activity IDs for time range filtering, could use significant memory. Mitigation, maybe a caching strategy. Keep most frequent leaderboards, global daily run, perpetually in Redis. Calculate less common ones on demand or with longer TTLs.
Okay, that wraps our deep dive into Strava.
All right, let's pivot. We just navigated fitness tracking. Now let's tackle something entirely different, but equally crucial in modern systems. Next up, designing a distributed cache, a critical component in almost all scalable systems today. E-commerce, social networks, you name it. This isn't just storing data, it's doing it across many machines for speed, resilience, massive capacity. This will be our exclusive focus now. ####1. Functional requirements. Just like before, we start by pinpointing what the system must do. These core functional requirements define the essential operations clients expect from our cache service.
First and foremost, the essence of a cache is managing key-value pairs. So users should be able to set, get, and delete key-value pairs. This is the fundamental CRU capability, right? How data goes in, how it's retrieved, how it's removed.
Exactly. Beyond basic storage, a crucial feature for any effective cache is configuring expiration time for key-value pairs, often called time to live, or TTL. This lets data automatically become stale, get removed after a period, keeps the cache fresh, frees up memory, prevents it growing indefinitely with old stuff.
And finally, when the cache inevitably fills up, especially in memory, we need a clear policy for deciding what gets kicked out to make space. So data should be evicted according to at least recently used, or LRU, policy. Items not accessed for the longest time get removed first, assuming they're less likely to be needed soon.
Correct. Worth noting, LRU is chosen here. Very common, very effective. But in a real interview, always confirm. Other policies exist. LFU, least frequently used. FIFO, first in, first out. Custom ones might be better depending on the workload. As for what's below the line here, we're not letting users configure the overall cache size. That's usually an operational parameter managed by admins, not an end-user function. #####2. Non-functional requirements.
Okay, we know what it needs to do. Now, how well does it need to do it? These non-functional requirements are especially critical for a distributed cache, designed for high performance, massive scale, often vital for app responsiveness.
Indeed. First core requirement, fundamental for any distributed system, high availability, needs to stay operational even if individual nodes fail. For a cache, it's generally acceptable for eventual consistency to be the model. Key distinction. Gives us more flexibility in design, allows higher performance than strong consistency. Data might not be identical across all replicas immediately after a write, but it will converge eventually.
And of course, speed is absolutely paramount. It's a cache. Primary purpose is serving data faster than the underlying store. So the system needs exceptionally low latency operations, targeting less than 10 milliseconds for both get and set. That's lightning fast. Demands highly optimized paths, minimal network overhead.
It truly is. Drives many architectural choices, pushing away from patterns with significant coordination delays, and crucially, massive scalability. Support storing up to 1 terabyte of data, handle a peak of 100,000 requests per second. These numbers define the challenge, dictate the infrastructure scale.
That's a huge workload. What's below the line for non-functionals?
We're not concerned with durability. Data doesn't need to persist across restarts or power failures. If the cache clears, that's okay. The source of truth is elsewhere, usually persistent DB.
Right, it's a cache, not a primary data store.
Exactly. Also, explicitly not aiming for strong consistency guarantees adds complexity, unwanted latency. Complex querying beyond simple key-value lookups. Also out. Transaction support, multi-atomic updates. Not in scope either. These assumptions are vital to confirm in any design scenario, as they dramatically influence the entire design, from data structures to distributed protocols. ###3 capacity estimation.
Okay, non-functional set. 1 terabyte data, 100K request sec peak. Let's crunch some numbers. Translate these into concrete infrastructure needs. How many servers do we need?
For throughput, let's make a reasonable assumption. A single, well-optimized cache host, typical cloud hardware, can do maybe 20,000 requests per second. Target is 100K recs. So 100,000 divided by 20,000 per node equals 5 nodes. But you need buffer for spikes, failures, maintenance, a plan for maybe 8 nodes minimum to reliably handle throughput.
Makes sense for throughput. Now, storage capacity calculation, often the dominant factor for cache node count, right?
Typically is, yeah. A typical cloud instance, say 32 GB RAM, can't use all of it for cache data.
Yeah.
OS, cache software, overhead. Maybe reliably use 24 GB for actual cache data. Requirement is 1 terabyte, 1024 GBP. So 1024 GBP divided by 24 GBP per node comes out to about 42.67. Round up to 43 nodes. Again, add a safety margin for growth, overhead. Plan for around 50 nodes conservatively.
So 8 nodes for throughput, but 50 nodes for storage. Storage requirement is clearly the limiting factor here.
Exactly. Conclusion. Provision based on storage needs. Plan for 50 nodes for the 1 TB storage. This higher node count inherently provides ample headroom for throughput, way more than the minimum 8 needed. Important reminder. These are rough, high-level estimates, depend on instance types, value size, read-write ratio, replication, growth, but gives a solid quantitative starting point for design and resources. ###4. Core entities.
This section might seem almost trivial for a cache, but good to formalize. What are the core entities we're dealing with? Helps lay out the fundamental building blocks.
You're right, they're fundamentally simple, which is part of their power. The core entities are, well, keys and values. It's a key value store.
So the primary data we need to persist, mostly in memory, are unique keys and their associated opaque values.
That's precisely it. No complex relations, no foreign keys, just key maps to value. In an actual interview, you'd acknowledge this is straightforward, maybe state them, confirm that's the expected level of detail for entities. Saves valuable time for the more complex parts, high-level design, distribution, deep dives. The simplicity here lets us focus complexity elsewhere. #5, API or system interface.
Similarly, the API for a distributed cache is usually quite straightforward, but crucial to define explicitly early on. Guides high-level design how clients interact. Based on functional requirements, what are the fundamental operations?
We need the 3 primary cache operations mapping directly to requirements: set, get, and delete the basic contract.
So to set a key value pair, insert new or update existing, use pust.key. Client sends request body with the value for that key, writes data in.
To get a key value pair, retrieve data using key, use gat.key. If key exists, server returns response body with the value, primary read operation.
And to delete a key value pair, explicit invalidation removal, delete.key would suffice. Explicitly removes data.
These APIs are indeed very straightforward, minimal, reflecting the cache's purpose. Key takeaway here, like the source material stresses, know where to spend your time in a design exercise. That's just simple. Move through them efficiently. Dedicate more time to the real complex challenges. Distributed systems, scalability, performance. That's the real meat of this problem. ###Tech6, high-level design.
Okay, requirements, interfaces covered. Let's start building our cache, beginning with an MVP, a minimum viable product. Focus on satisfying core functional requirements for a single node first. Don't worry about distribution or demanding non-functionals yet. Build that foundation.
Exactly. First requirement. Users should be able to set, get, and delete key value pairs. At its core, any simple in-memory cache uses a hash table. Think Python dict, Java hash map, Go map. Ideal because they offer average 0.1 time for lookups, inserts, deletes, incredibly fast.
So on a single server, you'd have a cache class, internal data dictionary map, exposes methods, det key returns data key, set key value, assigns data key value, delete key, removes data key. Simple as that for one instance.
Precisely right, all highly efficient. Hash table implementation handles collisions, resizing, abstracts that away. Host this code on a single server, API requests get parsed, call the right cache method. This basic design works for fundamental key value ops. Solid foundation, though not production ready for real traffic or large data yet.
Next, requirement 2. Users should be able to configure the expiration time for key value pairs, be time to live, TTL functionality. Entries disappear automatically after a duration.
For this, instead of just storing value, we store tuples. Value, expiry timestamp. Expiry timestamp is current time plus TTL. In get, before returning, add a check, compare current time with stored expiry timestamp. If expired, current time expiry, delete the entry from data, return null, key no longer valid, set method takes optional TTL parameter. If provided, calculates expiry at current time plus diddle, stores value expiry. If no TTL expiry, it can be null, never expire.
So simplified get, value expiry, data key, check if expiry and current time expiry. If true, delete data key, return null, else return value for set expiry current time plus siddle if TTL present and data key value expiry.
That's the logic. But this basic TTL has a problem. Expired keys only get cleaned up when accessed. Cache can fill with stale entries no one requests, memory bloat, reduced efficiency. Solution.background janitor process or scavenger.cleanup function runs periodically fixed schedule every minute or when memory pressure high, stands for and removes expired entries. Classic trade-off, CPU usage, scanning versus memory efficiency, keeps cache lean.
Okay, basic ops, active TTL management. Final high-level requirement. Data should be evicted according to LRU policy. What happens when cache fills, even with TTLs, need space for new items? Remove least recently used.
Classic data structure challenge. Need 2 things. Super fast 0.1 looks inserts and efficiently track update recency for LRU eviction. Simple hash table. 0.1 lookups, no order tracking. Simple list.tracks order, but lookups ordering slow. Elegant solution combine both. A hash table and a doubly linked list.
So how do these two work together for O1 on everything?
The hash table, our data map, stores key/node mapping. The node is in the doubly linked list, holds actual value and expiry. O1 lookup of any item by key. The doubly linked list maintains access order. Use dummy head and tail nodes to simplify edges. Head, right after dummy head, most recently used. Tail, right before dummy tail, least recently used. Operations, all one. Add set item, new key. Create node, key, value, expiry. Add to hash table, key, nash node. Insert node at fronted links list after dummy head, most recently used now. If size capacity after adding. Evict. Remove least recently used item, the node right before dummy tail. Remove from both list and hash table. Access existing item, get or update existing. Look up node and hash table. Oh, need to update recency. Remove node from current list position, 01, thanks to doubly linked pointers. Move that node to very front of list after dummy head. Now, most recently used.
And the clever part is all key ops get set, even LRU eviction stays super efficient at 01 by using the strengths of both structures. Forms the basis of a high-performance single-node LRU cache with TTL, hashtag tag 7. Deep dive.
All right, that's our robust single-node cache design. But remember, non-functional requirements specified a distributed cache. 1 TB data, 100K recs, high availability. Now, the real system design challenge: transform this single node into a truly distributed system. Address scale, fault tolerance, performance.
First deep dive then. How do we ensure our cache is highly available and fault tolerant? A single node is a single point of failure. If it goes down, cache gone. Impacts dependent apps. Key challenge, fundamental to distributed systems. Data replication. Multiple copies of cache data across different nodes for redundancy.
Raises crucial questions. How many copies? Which nodes store them? How to sync them as data changes? What happens when a node fails? Several fundamental replication patterns exist, each with trade-offs.
Let's start with synchronous replication. Maintain a few replicas, copies of each data shard. Write update goes to all replicas simultaneously, synchronously. Client request only acknowledged after all replicas confirm they persist to the write.
Offers strong consistency. All copies identical at act time, but challenges are significant, especially for a high-performance cache. Directly impacts write latency, blocked until slowest replica responds. Impacts availability. If any replica is slow or down, entire write operation blocked for that data portion. Generally not suited for our cache, where we prioritize availability performance over strict immediate consistency.
So if synchronous is too slow, fragile for a cache, what's better when performance is key?
Much better fit. Asynchronous replication, often called primary replica or leader-follower. Write comes in, update one primary copy immediately. Write confirmed to client once primary acknowledges. Then changes propagate to secondary replicas asynchronously in the background.
Sounds much faster for writes.
Yeah.
Specific advantages for our cache.
Significant advantages. Better write performance, no waiting for replicas. Higher availability. Writes proceed even if replicas down. Scales better with more replicas. Don't impact initial write latency. Natural fit for caches where some temporary staleness, eventual consistency is acceptable. Primary data source isn't the cache anyway. Challenges though. Replicas may have stale data temporarily. Failure recovery is more complex. If primary fails, need robust mechanism to promote a replica to new primary. Ensure it has necessary updates from old primary.
And what about even more distributed, like a massive peer-to-peer store?
That'd be peer-to-peer replication. Every node is equal. Any node accepts reads-writes for data it's responsible for. Changes propagate via decentralized mechanisms like gossip protocols. Nodes exchange state updates with random peers.
Benefits for our cache.
Maximum scalability, availability. No single point of failure bottleneck. Writes processed immediately, async propagated. Challenge is considerable, though. Significantly more complex implementation. Each node connects to multiple peers, need robust conflict resolution if multiple nodes update same data concurrently. Eventual consistency inherent. Different nodes might temporarily have different values. Careful conflict resolution needed. For our cache, given requirements, async replication offers good balance, availability, performance, relative simplicity. Peer-to-peer offers max scalability but with substantial implementation overhead. Key is understanding trade-offs, choosing appropriately.
Moving on, deep dive 2. How do we ensure our cache is scalable? Single node won't cut it for 1 TB data, 100K recs. Need strategy to distribute load across machines.
Core strategy, partitioning or sharding. Split entire key value data set across multiple nodes. Each holds a manageable portion. Allows horizontal scaling. Need more capacity, add more machines. New machines take a share of data and load.
We already calculated node count around 50 based on storage. Critical question now. Given 50 nodes, how do we efficiently know which specific node a given key value pair should be stored on and retrieved from? Routing needs to be fast, consistent.
Leads directly to deep dive 3. How can we ensure an even distribution of keys across our nodes? Solution, fundamental to many distributed data systems, consistent hashing.
Right, because the naive hash key percent n equals node count works for a fixed n, but iterative a node. Modular changes mapping for almost all keys.
Yeah.
Massive, costly remapping, data redistribution, huge operational headache.
Precisely. Consistent hashing elegantly solves this. Conceptually arranges nodes and keys on a circular key space, a ring. Use a consistent hash function, murmur hash often preferred, fast, good distribution, to map node IDs and data keys to points on the circle. To find node for a key, start at key's position, move clockwise around ring, find first node. That node stores the key. Beauty is minimal disruption. Add a node, slots into ring. Only keys that now fall into its segment, previously mapped to next node clockwise, need remapping migration. Remove fail a node. Its keys redistribute to next node clockwise. Impacts only a small, localized portion. Minimizes data redistribution, network churn. Critical for high availability performance during scaling. To further improve balance, avoid hotspots, consistent hashing often uses virtual nodes. Each physical server maps to many less virtual nodes, distributed randomly on ring. Greatly improves data load balance, especially with few physical nodes or frequent changes.
Much more resilient for dynamic clusters. Now, what if we have a hotkey key being read a lot? Deep dive 4. What happens if you have a hotkey that is being read from a lot? Hot reads. Common challenge. Disproportionate read traffic creates hotspots, degrades performance for entire shard node.
Classic scaling reads problem. One simple but often inefficient approach. Just scale up hardware of affected nodes, or maybe all nodes. Upgrade CPU, memory, network.
But that sounds expensive, not targeted. Upgrading all nodes for a few hot ones.
Precisely. Expensive, inefficient, over-provisioning for entire cluster for a small subset problem, doesn't address root cause, unsustainable at scale. Another idea. Dedicated hotkey cache. Separate, smaller cache layer, maybe more powerful hardware, different network config. Just for hotkeys, hotkeys get promoted to this tier, maybe geographically distributed closer to requesting users.
Sounds more targeted.
Yeah.
But complexities too, I bet.
Definitely adds complexity. Consistency challenges between main cache and hotkey cache. Needs sophisticated monitoring, intelligent system to dynamically identify, promote, demote hotkeys based on real-time traffic. Significant operational overhead. We also discussed RID replicas earlier for high availability, multiple copies of entire nodes to distribute reads.
But again, replicating all data across many nodes.
Yeah.
Massive storage network overhead if only a tiny percentage of keys are hot. Blunt instrument.
Correct. So more targeted, often optimal approach for hot reads. Create copies of specific hotkeys. Selectively copy only the specific hotkeys across different nodes to distribute read load. Mechanism, monitor key access. When hot exceeds read threshold, system intelligently creates multiple copies of the key's value. Store with different internal suffixes, like user.123 tag 1, user.123 tag 2, user.1233 tag 3. Distribute these suffix keys via consistent hashing, landing on separate machines. Read requests. Clients randomly choose a suffixed key, e.g. product.iPhone gets 100k reads. Create 4 copies. Each handles 25k reads. Distributes load. Writes, though, critical aspect. All copies of a hotkey must be updated for consistency, even eventual. Main challenge, keeping copies in sync on change, adds write amplification. Best for read-heavy hotkeys. For read-write-heavy keys, consistency overhead can worsen the problem. Shows deep understanding of operational concerns, mitigation for real traffic patterns.
And speaking of hotkeys, what if a key is being written to a lot? Deep dive 5. What happens if you have a hotkey that is being written to a lot? Hot writes. Typically more complex than hot reads due to consistent cytovicity needs.
Indeed, hot writes have unique challenges. First, effective approach. Write batching. Instead of processing every write immediately, collect multiple writes for same key, or related keys, over short window, 50-100 meters. Apply all as single atomic update. Especially good for counters, metrics, logs, where final state matters more than seeing every individual increment. Example, viral video gets 10k view update sec. Instead of 10k individual writes, batch into 1 plus 1,000 views, update every 100 meters. Dramatically reduces write pressure. Benefits, significantly reduces write load, improves throughput. Challenges, trade-off between batching delay and write visibility. Update, not seen instantly. Complexity and failure handling during batching, best for eventual consistency scenarios.
Second approach for hot writes. Key sharding, specifically for a single hotkey. Split one conceptual hotkey into multiple distinct subkeys, distributed across nodes using suffixes. Views.video123 might become views.video123.1, views.video123.2, views.video123.10. Write arrives for views.video123. Randomly select one shard, views.video123.5 to update.
Effectively distributes write load. 10k write sec across 10 shards. Reduces per shard load to 1k opsec. Powerful way to alleviate write contention. Challenge is significant, though. Read operations become more complex. Need to aggregate data from multiple shards to get complete picture. Some views.video123.1 to 0.10. Potentially increases read latency resource usage. Trade write perf for read perf. complexity around consistency across shards during failures rebalancing. Most effective for easily decomposable ops counters, not suitable for ops needing strict ordering or atomicity across all updates to the conceptual key.
Finally, Deep Dive 6. How do we ensure our cache is performant? Single node was O1 in memory. Distributed system performance is about the whole ecosystem client to node and back.
Correct. Performance in distributed systems is about minimizing network latency, clients quickly finding connecting to right node, efficient request bundling, avoiding unnecessary network chatter bottlenecks. Many solutions already discussed help performance. Request batching for hot writes reduces network round trips. Consistent hashing for routing cuts latency. No central routing query needed. Client often calculates target directly.
What's a new consideration specifically for performance in distributed environment?
Critical aspect, connection pooling. Instead of setup teardown for every request, expensive network handshakes, TCP/IP, TLS, clients maintain a pool of open, persistent connections to cache nodes.
So connections are always ready.
Exactly. Ready-to-use communication channel available. Eliminates connection setup overhead per request. Seemingly small optimization drastically reduces average latency and, importantly, tail latencies, P95, P99 response times. Tail latency is crucial because they disproportionately affect user perception, especially under heavy load. Ensures smoother, more consistent experience even for slowest requests.
So tying it all together for our final distributed cache design, each node, hash table plus linked list for O1 LRUTTL, scaling, asynchronous replication, high availability hot reads, consistent hashing, sharding routing, random suffixes distribute hot rates, right batching and connection pooling, latency overhead reduction, truly robust, performant distributed cache architecture. We've just navigated the intricate world of distributed caches, seen how they underpin so many apps. Now let's unbox the system design behind a rapid local delivery service, like Gopuff. Imagine getting convenience store stuff delivered in under an hour from hyper-local micro-distribution centers. This deep dive will exclusively reveal the inventory and ordering magic behind the scenes for such a service. #1 Functional requirements.
As always, start by pinpointing core functionalities from the user's view. For a rapid local delivery service like Gopuff, functional requirements focus intensely on what the customer can actually do, especially regarding product availability and placing orders.
First, and critically important for any service promising speed and locality, customers must be able to query item availability. Not just if it's in stock generally, but specifically if it's deliverable within that tight time frame, like 1 hour, and by their specific location. Effective availability is really the union of inventory at nearby distribution centers, DCs, that can meet that promise. Need to know if those chips are not just in stock, but physically close enough for rapid delivery.
Absolutely. That 1 hour window is a hard user-facing constraint. Profoundly influences subsequent design choices. And then, once they find items, confirm availability, customers should be able to order multiple items at the same time. Seems obvious for shopping, but it's a distinct functional requirement. System must handle complex baskets correctly, atomically.
So flip side, what's below the line, out of scope here, keeps focus sharp.
Explicitly not handling payments, complex purchase workflows, separate specialized domain, financial integrations, fraud detection, payment gateways, whole other layer of complexity. Also not dealing with driver routing, dispatch, intricate logistics of physical deliveries, that's a whole other beast. Optimization problems with mapping, real-time traffic, dynamic scheduling.
And even though it's e-commerce-like, deliberately not touching complex search functionality, product catalog APIs, rich metadata, recommendation engines, this design is strictly concerned with core mechanics, item availability, and the atomic act of placing an order for those items.
And finally, post-order ops like cancellations, returns are also out of scope. Absolute emphasis here is specific, critical, accurately aggregating availability across local DCs, and crucially, letting users place orders in a way that absolutely prevents double booking the same physical product, ensuring inventory integrity. #2 non-functional requirements.
Now, non-functional requirements for our rapid local delivery. These are particularly demanding. Define essential quality attributes, especially given the rapid promise, high volume potential. Really test the design's robustness.
Indeed. Speed is paramount for availability checks. So availability requests users do frequently while browsing searching should be incredibly fast, ideally under 100 milliseconds. Low latency, crucial for use cases like real-time search filtering. Users browse many items, expect instant updates on what's available nearby.
But when ordering, where real-world inventory is allocated, strong consistency is absolutely key. Cannot, under any circumstances, let two customers buy the exact same physical product. Terrible user experience, customer dissatisfaction, massive inventory nightmares for the business. This no double booking rule is fundamental, non-negotiable.
Absolutely. That strict consistency requirement for orders is a primary driver for our transaction design. And scale system needs to support very large number of physical locations, products. Specifically, scale to 10,000 distribution centers, vast geographical footprint, manage 100,000 distinct items in catalog across all DCs. Lot of inventory to track efficiently.
And expected order volume for such a popular service. Immense. On the order of 10 million completed orders per day. Truly massive transaction load our system needs to process reliably, consistently.
The huge daily volume, yeah, requires robust, scalable transactional systems. As for what's below the line for non-functionals, not delving into broad, complex topics of privacy, security beyond basic auth, also explicitly not covering comprehensive disaster recovery plans, multi-region deployments, backup strategies, RPOs. These assumptions vital, always confirm with interviewer, dramatically impact design choices, complexity, hashtag 3 singular, capacity estimation.
So 10 million orders per day. Target transaction volume. But availability queries happen far more often as users browse search. Need to estimate that load, typically much higher, impacts front-end responsiveness?
Let's do a quick back-of-the-envelope calculation to quantify that. Assume, on average, each user who eventually orders looks at maybe 10 different pages or performs 10 availability-related actions, search, browse, view details, before purchasing. And let's conservatively assume only 5% of users who query availability actually purchase. That's our conversion rate.
Okay, so if 10 AMS orders a day, and a typical peak day has maybe 100K seconds, common assumption, 12, 14 peak hours, 3,600 share safety factor, 100K.
Right.
Calculate base order sec.
Correct. Calculation for availability query a sec. 10 million orders day, 100,000 peak seconds day. 10 page checks per order, 0.05 conversion rate. Yield an estimated 20,000 queries per second for availability.
Wow, 20,000 queries per second. Very substantial read query load. Indicates clear, immediate need for significant scaling solutions for our availability service right from the start. Not a small problem. Implies read path needs aggressive optimization, distributed architecture.
Definitely highlights availability service will be under heavy continuous load. This capacity estimate is critical. Directly tells a simple single database read model won't suffice. Absolutely need robust architectural patterns, caching, read replicas, intelligent data partitioning to handle this traffic, meet latency requirements, hashtag 4, core entities.
Let's define the core nouns for this local delivery service. Not a full data model yet, just identify high-level entities, essential building blocks for the rest of the design, shape our thinking.
For this problem, a truly crucial distinction, fundamental to e-commerce inventory systems, between an item and inventory. An item represents a type of product customers care about: Cheetos, Coca-Cola, batteries, general product definition in a catalog.
And inventory, that's the physical count, the actual units available.
Precisely. Inventory represents a specific physical instance of an item located at a particular distribution center, DC. When we determine quantity available for an order, we're effectively summing these individual inventory instances for a given item across relevant DCs. So you order a Cheetos item, what gets fulfilled is a specific inventory unit of Cheetos from a specific DC.
Okay, perfect sense. Then we have the distribution center, or DC, critical geographical entity. Physical warehouse micro-fulfillment center where items are stored. DCs determine which items are available based on proximity, delivery capabilities. All our inventory is physically housed in these DCs.
And finally, the order entity represents a collection of inventory items successfully requested, allocated by a user for purchase delivery. Encompasses all necessary details: specific inventory units promised, user shipping billing info, overall status. By starting with these concrete, physical, business-critical entities, working towards more abstract ones ensures we capture all essential components the system needs to model and manage. Hashtag 5, API or system interface.
Core entities defined. Let's quickly outline APIs needed for primary functional requirements. Keep it simple, direct. Define the essential contract between client and backend without getting bogged down in implementation details yet.
For getting item availability, key discovery phase for user, need GATE availability endpoint. Client initiates. Takes crucial query params. Lat long for user location. Optional keyword if user searching. Standard page, page size for pagination, manageable chunks. Returns array of item availability objects. Item details, available quantity within user's serviceable delivery radius.
Then user selects items ready to commit. To actually place an order, have POST order endpoint. What's in the request body?
Request body for placing order contains two main things: First, user's current location, lat long again, crucial for revalidating 1-hour promise at submission time. Second, an array of items. Each object specifies item ID and desired quantity. On successful processing, it returns newly created order object, unique ID, initial status. Important to reiterate, user's location passed to both availability and order APIs. For order API, crucial not just for delivery, but to reconfirm at purchase moment that inventory is still available nearby, can genuinely be delivered within 1 hour. These simple APIs efficiently cover core functional requirements, serve as direct interface for client interactions. Hashtag 6, high-level design.
Let's delve into high-level design. Start with how customers query item availability by location. 2 distinct but connected steps. Efficiently find nearby DCs that could serve user, then check their inventory for requested items. Both need to be super fast, under 100 meters total.
For step 1, finding nearby DCs, initial thought, simple internal API, takes lat long, returns DCs within plausible 1-hour radius. Could use crude distance calc, Euclidean or better, have seen, and a threshold. Basic DCs table with lat long, query for distance, forms a primitive nearby service.
But as the crow flies, doesn't account for real-world stuff. Traffic, roads, barriers, one-way streets, all impacting our crucial 1-hour delivery promise. Simple distance needs refinement and a deep dive, right? Fundamentally insufficient.
Exactly. For step 2, checking inventory of these identified nearby DCs. Query primary database. Contains inventory table, physical counts at DCs, items table, product catalog. Assume Postgres initially. Joy A in inventory with item to get name description available quantity. Aggregate and return union of available inventory from serviceable DCs found in step 1. Note, catalog often separate from inventory in large e-commerce. Here, co-located for simplicity, but valid point for later discussion. So putting availability flow together. User requests availability, items A, B, C from location XY. Request hits availability service requests nearby service with users XY, nearby service returns list of deliverable DCs, availability service queries a database with these DC IDs, results summed, returned to client.
That sets up the read path. Now, second, critical requirement. Customers should be able to order items. Core is drawn consistency to prevent double booking. Need to check inventory, record order, atomically update inventory, item no longer available. Problem. Promising same inventory to 2 users simultaneously requires robust locking or transaction mechanism.
One potential approach. Separate databases for inventory and orders. Order placed. Acquire locks on inventory records, inventory DB. Create order record, orders DB. Decrement inventory release locks. Seems appealing initially. Maybe use best store for each. Fast in memory for inventory, relational for orders.
But I see potential nasty failure modes, like the source says. What if service crashes after order created but before inventory decremented? Subsequent user gets promised already taken inventory.
Precisely. Requires complex sweep jobs, reconciliation to identify reverse bad orders. Also, if multiple users order items with overlapping needs, user 1 wants A and B, user 2 wants B and A. Easy deadlock potential if locking isn't meticulous across separate systems. Need to explicitly design handle these complex failures. Significant architectural operational overhead.
So, preferred, more robust, often simpler option for that crucial, strong consistency.
More robust, often preferred. Singular Postgres transaction. Co-locate both orders and inventory in same relational DB, like Postgres. Fully leverage built-in ACID properties, specifically serializable isolation level. ACID. Atomicity, consistency, isolation, durability guarantees reliable transactions. Serializable is strongest isolation. Concurrent transactions behave as if sequential. Prevents dirty reads, non-repeatable reads, phantom reads. Means if 2 users try ordering same item simultaneously, Postgres Transaction Manager ensures only one succeeds. The other fails because inventory won't be available during first transactions log.
What's simpler? Entire order process either fully succeeds or fully fails as a single atomic unit. No partial states to worry about.
Exactly. Let's walk through the detailed order flow with Postgres transactions. User requests order, items A, B, C. Request goes to order service. Order service initiates single atomic DB transaction to Postgres leader. Inside transaction die. First, checks inventory table. Confirm available quantities for A, B, C, 0A. First, checks inventory table. B, if any out of stock, entire transaction rolled back, fails immediately. No partial allocation. A first checks inventory table.c. If all in stock, records order details. Crucially, updates status for those specific inventory items, decrement quantity or change status to ordered reserved in inventory table.
Cool.
First checks inventory table. Concurrently, new row created in orders table and order items table detailing new order. First checks inventory table D. Finally, if all steps successful, transaction committed. If transaction succeeds, Orders, service returns, created order details to user.
Obvious downside. If just one item in multi-item order becomes unavailable, entire order fails, forces user reselect. But generally better than partial nonsensical order or worse, double booking.
Absolutely. Clear trade-off. Higher integrity over user convenience in that edge case. Return meaningful error message. Guide user to try again or remove unavailable item. So, putting initial solution together. 3 services. Availability service, orders service, shared nearby service. Both avail orders use nearby for DC lookup. Single Postgres DB or clustered primary replica for inventory and orders partitioned by region. Availability service reads via read replicas for speed. Order service writes to leader using atomic transactions for strong consistency. Solid foundation for our local delivery service. #7 deep dives.
All right, robust, high-level design in place. Let's tackle critical deep dives to refine, scale our local delivery service. Initial availability use simple geodistance, but core promise is 1-hour delivery. First deep dive. Make availability lookups incorporate traffic and drive time.
Crucial refinement. Simple distance calcs, Euclidean, Haversian, fail to account for real-world complexities. Traffic, road conditions, one-way streets, barriers, rivers, mountains, urban density, all impact our 1-hour drive time requirement. Functional requirement is drive time, not as crow flies.
So the basic simple SQL distance approach we started with. Useful first pass, but those significant challenges mean it's unsuitable for a firm 1-hour guarantee.
Exactly. Immediate next thought, maybe a travel time estimation service. Periodically sync DC lat-long data into service memory every 5 minutes. Keep DC locations up to date. User queries availability. System queries external, specialized travel time estimation service. Google Maps API, OpenStreetMap routing engine. For precise travel times from user location to each and every potential DC. Iterate over all DCs, filtered down to those truly within 1 hour.
Immediate challenge I see. Way too many queries to that expensive external service. 10,000 DCs. User queries. Hit external API 10,000 times. Most DCs aren't plausibly within 1 hour. Incredibly inefficient. Costly.
You hit the precise bottleneck. Optimal approach combines efficiency and accuracy. Pruning candidates plus travel time service. Builds on previous idea. Still periodically sync DC data to memory for fast local lookups. But when user location comes in, before hitting expensive external service, first prune candidate DCs. Apply a fixed, generous geographical radius, e.g. 60-mile circle, most optimistic possible 1-hour drive. Only consider DCs within this initial rough circle. Only these restricted, plausible candidates are then passed to external travel time service for final, precise, accurate estimation, incorporating real-world factors.
Dramatically reduces expensive external API calls. Makes feature viable at scale. Next deep dive. Make availability lookups fast and scalable. Estimated 20,000 query ESIC earlier. Huge read load. If it all hits primary DB, major bottleneck, violates sub 100 meters latency, non-functional.
Classic scaling reads problem, absolutely critical. Inventory availability queries, as you noted, vastly outnumber actual purchases. Therefore, aggressive caching with short TTLs isn't just helpful, it's absolutely critical for meeting performance targets.
First, most straightforward approach. Add a Redis cache in from database for availability data. How does flow change?
Availability service first queries Redis. Cache it. Data in Redis not expired. Return result immediately. Lightning fast response. Cache miss. Availability service performs underlying lookup on primary DB, gets data. Then, crucially, writes results into Redis with the set TTL before returning to client. Set relatively low TTL, 30s 1 minute for freshness as inventory changes. Main challenge, cache invalidation. Order service, whenever it writes to inventory table, item purchase, stock, decremented, must explicitly expire and validate affected cache entries in Redis. Ensures cache reflects most up-to-date inventory or quickly refreshes.
What other strategies complement caching for high performance and scalability for availability?
Postgres read replicas and partitioning also key strategies for scaling reads on DB layer itself. Since we only read inventory from nearby DCs, for a user can logically group nearby DCs by region ID, maybe first 3 zip digits, or larger geo partition. Partition underlying inventory DB based on these region IDs. Query for user in specific region typically only needs to access 1 or 2 specific DB partitions, not scan entire data set across 10K DCs. Significantly reduces scope of each DB query. And then read replicas. Use them to offload immense read burden from primary DB leader. Use multiple read replicas specifically for availability queries. Small inconsistency, few seconds delay in count, generally tolerable for availability check. Vast majority of availability reads go to replicas, leaving Postgres leader free for critical, strongly consistent writes from order service. Challenges: managing replica sizing for traffic, managing data partitioning to avoid overloading any one replica or creating imbalanced partitions.
So, Optimal final solution for nearby availability service. Combines multi-layered approach, aggressive Redis caching, immediate responses, coupled with Postgres for replicas and intelligent data partitioning on backend. Layered, comprehensive approach essential for serve like Gopuff to operate at required speed scale, handle 20K QPS, maintain inventory accuracy for orders. To wrap up our deep dives into complex systems, we're plunging into the high-stakes world of a scalable trading platform like Robinhood, not just stocks. It's real-time data, lightning-fast orders, ensuring rock-solid consistency in a highly dynamic, financially sensitive environment. We'll exclusively explore how they manage live price updates, intricate order flow.
It's a truly fascinating, demanding domain. Milliseconds can mean millions. First, crucial context. Platform like Robinhood is fundamentally a brokerage, not an exchange. Doesn't directly facilitate trades between buyer-sellers in open market. Instead, routes trades through external market makers or exchanges entities handling actual order matching, filling, cancellation. For simplicity, assume external exchange API available. Provide synchronous request-response API for placing canceling orders. And a trade feed, continuous stream, or webhook pushes real-time data back every time trade occurs. Feed includes symbol, price, shares, unique external ordered from exchange. #1 functional requirements.
So what does a Robinhood-like brokerage need to do from user perspective? Core functional requirements revolve around real-time market data, comprehensive order management.
First, absolutely fundamental for any trading platform. Users must see live prices of stocks. Without immediate up-to-the-second market data, informed trading decisions impossible. Real-time price feed, critical for active traders, passive investors alike.
And second, once they have market data, users need to manage orders for stocks, covers full life cycle, create different order types, market orders execute immediately at market price, limit orders execute at specified price or better. Also crucially, ability to cancel outstanding orders not yet filled. Basic operations trader needs to interact with market.
As for what's below the line, out of SOAP. Explicitly not allowing users to trade outside standard market hours. Simplifies handling pre-market after hours, order states, queues, market mechanics.
And keep focus on stocks.
Yeah.
Not dealing with other, often more complex financial instruments, ETFs, options, crypto, bonds. Each introduces unique trading rules, data requirements.
Also, users won't see full granular order book in real time. Order book displays all pending buy-sell orders at various price levels. More advanced feature requires different, even higher level of data granularity throughput. Beyond scope of this deep dive, focus remains squarely on presenting live prices, facilitating order placement cancellation. #2 non-functional requirements.
Now for the non-negotiables. Non-functional requirements. Particularly critical for trading platform where trust, financial accuracy, speed are paramount, fundamentally shape our architecture.
Indeed. First core requirement, perhaps most vital for financial app. System must prefer high consistency for order management. Absolutely essential users see accurate, up-to-date, consistent order info when making financial decisions, placing trades. Discrepancy in order status, missed update, incorrect balance, severe financial implications for user, legal ramifications for brokerage. Avoid ambiguity here.
And of course, scale is paramount. System must scale to handle extremely high number of trades day, 20M daily active users, average 5 trades day across thousands of symbols. Quickly accumulates into truly massive potential load system must absorb reliably.
That volume certainly drives need for immense throughput capabilities, and latency just as crucial in trading. System needs exceptionally low latency reflecting simple price updates and critically placing orders, aiming for under 200 milliseconds end-to-end. In trading, every millisecond counts. Market conditions change instantly.
And crucial financial operational consideration. System should strictly minimize number of active clients connected to external exchange API. Exchange data feeds, individual client connections, typically very expensive resources, billed by connection data volume. Consolidating, optimizing external communication is major cost-saving performance factor.
This point absolutely vital for cost efficiency, operational stability. As for what's below the line for non-functionals, not designing for connecting to multiple exchanges simultaneously complicates routing, pricing aggregation, execution. Not managing intricate trading fees, commissions, complex calcs. Explicitly not enforcing daily trading limits, nor tackling sophisticated challenges like protecting against bots, market manipulation, significant security or risk management challenges. These non-functionals, subtle as they seem, truly characterize underlying complexity lurking behind deceptively simple user features on a trading platform. #3 capacity estimation.
Let's quickly quantify the sheer scale for a platform like Robinhood. Put non-functionals into concrete numbers for orders, data, daily active users, DAU, 20 million,
And assume, for estimation, average active user makes 5 trades day. Reasonable average accounts for active day traders and casual investors.
So total potential orders day. If every DAU makes those average trades, staggering calc, 20 million users, 5 trades day equals 100 million potential orders per day system needs to handle.
Absolutely immense volume. Implies very high throughput system, not just desired, but fundamentally required. Not just for order processing, but handling vast real-time market data across thousands of symbols. Capacity estimate directly drives need for exceptional scalability, extremely stringent low latency across every component. Data ingestion to order execution tells us need robust distributed solutions for sustained, very high transaction rates. ###tag for core entities.
Laying foundation with core entities crucial. High-level nouns defining systems' fundamental concepts, primary data objects it manages. Don't need every DB column yet, but identifying basic building blocks essential for shaping architecture.
For a trading platform like Robinhood, primary entities, quite straightforward, directly reflect core interactions. First, user entity. Represents distinct individual using brokerage system. Contains basic profile info to identify them.
Then, central to trading. Symbol. Represents specific tradable asset, stock like Meta, AAPL. Unique identifier for financial instrument users, buy-sell.
And finally, most important for brokerage, order entity. Represents concrete instruction requests from user to buy-sell specific quantity of symbol at given price condition. Encapsulates all necessary details. Type, market, limit, quantity, price, current status. These 3, user, symbol, order, form absolute backbone of trading systems' data model interaction patterns. #tag5 API or system interface.
API is primary way users interact, allowing mobile as web interfaces to talk to backend. Defining interface early guides high-level design. Define endpoint for each core functional requirement for comprehensive coverage.
To let users see live prices, retrieve stock details. Get symbol.name endpoint. Name and path is stock symbol. Resample symbol A APL. Returns symbol object, relevant static info, company name, sector, and current live price data.
Then, managing orders, core transactional capability. To create an order, use post order. What's in request body?
Request body JSON payload contains crucial fields, position, buy or sell, stock symbol, example Meta, price instance, critical in finance to avoid float precision issues, prices as integers, $522.10, 522.10. Quantity, endpoint returns newly created order object, unique internal ID, initial status, on success.
To cancel an order still outstanding, delete order.id straightforward effective. ID path is unique order ID to cancel. Unsuccessful receipt processing returns simple success confirm maybe is true.
And finally, let users list all their orders. History, open positions. Get orders. Retrieves paginated array of order objects. Client efficiently displays potentially a large number of past current orders without overwhelming network.
Crucially, for all these APIs, user auth's paramount. User info, session token, JWT, securely passed in HTTP headers. Standard, secure practice for authenticating authorizing requests. Ensures only legitimate user accesses, modifies own data. Avoids less secure method of passing sensitive user info and request body. #6, high-level design. All right, let's start piecing together our Robinhood-like system. Build sequentially, address functional requirements one by one. First up, users can see live prices of stocks. System needs efficient real-time price display for 1 mini stocks, low latency, 200 meters, minimize expensive exchange connections.
Let's consider simplest but flawed initial approach, client polling exchange directly. Each client app directly polls external exchange API every few seconds for symbols user interested in, updates UI.
Immediately see UI problematic, incredibly inefficient, costly.
It is. Several reasons. First, massive redundant exchange calls. Many clients request exact same price info, popular symbols, even if price unchanged. Hugely inefficient. Our backend, external exchange, high data costs, potential rate limiting. Second, updates inherently slow. Responsiveness dictated by client polling interval. Meet 200 meters SLA, poll every 200 meters, absurdly high frequency for external API, quickly overwhelm it, definite non-starter for scalable brokerage.
So need to centralize external communication. Slightly better. Client polling, internal symbol service, proxying exchange. Client polls, internal symbol service we control. Symbol service does quick key value lookup on internal cache, stores latest prices. Cache kept up to date by dedicated symbol price processor listening to exchange's real-time feed.
Indeed an improvement. Centralizes expensive external communication. Only symbol price processor connects to exchange feed. Internal symbol service acts as proxy. However, fundamental polling problem remains between client and internal service. Still wasted HTTP traffic if prices don't change. Polling intervals still dictates worst-case user latency. Better, but not optimal for true real-time responsiveness.
So, optimal solution for real-time price updates. Low latency, efficient resources.
Optimal solution. Server-sent events, SSE. Provides persistent unidirectional HTTP connection. Server continuously pushes live price changes to client instantly as they occur. Often superior to full web sockets when client primarily receives data streams, doesn't send much back, like live price feed. SSE is simpler to implement manage for this one-way flow than WebSockets. With SSE, rework API, PST subscribe endpoint. Client send request with list of symbols to subscribe to. Backend sets up maintains SSE connection between client and specific symbol server instance. On connection, symbol service immediately sends initial list of current prices for subscribed symbols from cache populated by symbol price processor. As symbol price processor gets new trade data price updates from exchange, it publishes internally. Symbol service instances receive updates, efficiently push over respective SSE connections to all subscribed clients. Near instantaneous price reflection.
Sounds far more efficient for real-time delivery. Push data only when changes. But challenges maintaining millions of persistent connections. Needs specific load balancer configs, sticky sessions, robust handling for disconnects, reconnects gracefully. Plus, routing user connections, symbol data efficiently to correct symbol service instances key. Need deep dive on that.
Absolutely. Crucial operational challenges. Now, second core functional requirement. Users can manage orders for stocks, create market limit orders, efficiently cancel outstanding, provide comprehensive list of user orders.
Again, naive client directly interacting with exchange would be disaster.
Catastrophic. First, allowing direct client interaction, massive, unmanageable number of direct exchange connections requests. Incredibly expensive, quickly exhaust allocated limits. Second, no clear, reliable path for client to check order status beyond constant polling exchange. Inefficient. Third, client solely responsible for tracking orders. Unreliable local storage memory. Completely unacceptable for financial transactions. Absolutely not viable for professional brokerage.
So, need intermediary service. Common pattern for decoupling handling spikes. Order service, queue order dispatch service. Order service receives requests, validates unqueues orders, Kafka, RabbitMQ. Order dispatch service picks up, processes asynchronously. Queue prevents dispatch service overload, allows elastic scaling.
Pattern excellent for many async workflows. But critical problem for trading platform, breaks strict latency SLA 200 meters for order placement. If queue builds up under heavy load, orders experience significant unpredictable delays before submission. Disastrous for time-sensitive trades, few seconds delay, profit loss difference, or failed cancellation.
Leads to optimal approach for order management. Order service batch order dispatch gateway. Order service receives client requests, performs all business logic validation, funds, rules, then sends orders directly, synchronously to order dispatch gateway.
Gateway, managed service like AWS NAT Gateway or custom proxy, acts as centralized outbound comms point, enables internal services to talk to external exchange efficiently, makes all requests appear from small, controlled set of IPs, helps exchange side rate limiting whitelisting. Order service handles core business logic, scales based on order volume. High-frequency system like this needs sensitive auto-scaling or, more likely, over-provisioning for sudden spikes without adding latency. Challenges. Order service needs to be incredibly efficient. Client interaction, asynchronous exchange interaction, might use internal connection pooling, potentially batch multiple user orders for same symbol into single larger requests to exchange if API supports it, further optimizes external comms.
Now, orders submitted processed. How store them so users see history status via GKT orders?
Need dedicated order database, relational DB, Postgres, ideal choice, primarily for strong ACID guarantees, handling complex relational data consistently. For scalability, fast querying, horizontally partitioned, most logically by user-ID. Ensures all order updates reads for specific user happen on single DB node, user's partition. Keeps queries efficient, avoids cross-partition joins for common ops. Order entity and DB stores all relevant info. Symbol, shares, price, order type, internal status, pending, submitted, fill, canceled, critically, external ordered from exchange upon submission. To keep internal orders updated with real-time market activity, dedicated trade processor fleet, visualize a single component for simplicity, continuously tails exchange's real-time trade feed. Processor receives trade confirmations, then updates status of internal orders, reflects fills, partial fills, cancellations as they happen on exchange. How processor concretely reflects updates is key deep dive. Hashtag tag 7. Deep dives.
All right, let's dive deeper into core complexities of this scalable trading platform. First up, how can the system scale up live price updates? Efficiently propagate real-time updates to potentially millions subscribed via SSE, ensure updates routed efficiently to correct symbol service servers.
Robust solution. Leverage Redis PubSub. Publish subscribe. Redis incredibly fast, in-memory store, offers highly efficient messaging system. PubSub model, publishers, symbol preprocessor, send messages to designated channel. Subscribers, symbol service instances, receive all messages published to channels they listen to.
Let's walk through full workflow with Redis PubSub.
First, user client sends POST subscribe request to a symbol service server with symbols list. The server instance maintains in-memory mapping. Symbol set user tracks which connected SSE clients want which symbols. Second, symbol service server itself manages subscriptions to Redis PubSub channels. For each unique symbol, at least one connected user subscribed to server subscribes to corresponding Redis channel, e.g. symbol.price.meta. Only subscribes if doesn't already have active subscription. Consolidates external Redis subs. Third, market data comes in. Symbol price changes on exchange. Dedicated symbol price processor, ingesting exchange feed, immediately publishes new price update to relevant Redis PubSub channel for that symbol. Very fast, fire and forget op from processor. Fourth, efficient fan out. All symbol service servers subscribe to Redis channels for symbols their users care about. Every server subscribed to that symbol's channel instantly receives update from Redis. Highly efficient fan out at internal service level. Finally, symbol service receives update, fans out price update to all its connected SSE clients encrypted in that specific symbol. Near real-time updates to user device. User unsubscribes, disconnects. Heartbeat explicit. Server removes from in-memory set. If no more users on that server want a symbol, server gracefully unsubscribes from Redis channel, optimizes resource usage, benefits, scales beautifully, distributes load across symbol service fleet, efficiently fans out updates only to interested parties, self-regulating for managing update flow.
Very elegant pattern for real-time fan-out. Second deep dive, critical coordination challenge. How does the system track order updates? How does trade processor gets updates from Exchange efficiently update correct order in OrderDB? Tricky because OrderDB partitioned by userid, but Exchange feed only gives external ordered, not internal ordered or userid. Classic identifier mapping problem in distributed systems. Trade processor needs fast way to translate external ID into internal ordered userid pair to know exactly which DB shard specific order to update. Solution introduce separate key value store for mapping. Deploy new, highly performant dedicated key value store, RocksDB embeddable, Cassandra distributed NoSQL, specialized fast lookup service backed by memory optimized DB. Sole purpose map external ordered key from Exchange to internal ordered user-ed people. How does this mapping store get populated? How does trade processor use it?
Populated by order service at order creation time. Immediately after order successfully submitted to Exchange, receive external ordered back. Order service persists this mapping into new key value store, ensures mapping available before trade processor might need it. Then, trade processor receives trade update from Exchange feed, only contains external ordered. Efficient flow. 1. Trade processor uses external order for quick O1 lookup in dedicated key value store. 2. Lookup instantly retrieves corresponding ordered usered for internal order. 3. With userid, trade processor knows exactly which horizontally partitioned shard of order DB to connect to. 4. Looks up specific order by ordered within that shard. 5. Updates, orders details, status to filled, partially filled, fill price, quantity filled. Entire process enables highly efficient lookup, precise updates of internal orders based on external feed. Bridges gap between external and internal identifiers seamlessly.
Third, arguably most critical deep dive. How does the system manage order consistency? Paramount orders consistent on our side and Exchange side. Fault tolerance key due to financial implications.
Right, where rubber meets road. Primary order storage. Horizontally partitioned relational DB, Postgres. Partitioned by userid. Ensures all order updates reads for specific user happen on single DB node, user's partition. Crucial for transactional consistency performance without complex distributed transactions across shards for individual users.
Let's walk through order creation workflow step by step, carefully considering failure mitigation at each critical juncture.
1. Store order in DB with pending status. First, crucial. Very first step. Create order record in order DB status pending. Vital. Internal record of user intent before interacting with external Exchange. DB failure here. Respond client fail, stop workflow. Order never recorded internally. 2. Submit order to external Exchange synchronously. Order service sync submits pending order to external Exchange API. Immediately wait for response, hope for external ordered. Exchange submission fails, network issue, Exchange rejects. Immediately mark order failed and order DB respond client error. 3. Write external order to key value DB and update order in order DB to submitted. Exchange submission successful, got external ordered. Perform 2 crucial updates. Write external order to dedicated key value mapping store. Update order status and order DB from pending to submitted. Failure mitigation. Here, critical. If this update fails after exchange submission succeeded, internal DB down temporarily. Inconsistency. Order on exchange, internal status pending. Resolve with robust cleanup background job. Periodically scans order DB for orders stuck pending too long. For each, uses client order, unique ID sent to exchange as metadata, to async query external exchange. Cleanup finds order did go through, retrieves external order, updates internal status to submitted, exchange confirms order didn't go through, marks internal order failed, ensures eventual consistency. 4, respond to client successful. All steps complete successfully. Respond client success, confirm order submitted.
Now, equally critical order cancellation workflow. Consistency there.
Cancellation follows similar fault-tolerant logic. 1. Update order status to pending cancel first. User requests cancel, very first action. Update status and order DB to pending cancel. Immediate internal update, crucial. Track cancellation attempts, resolve failed cancels later. Internal status update fails, respond client fail, stop. 2. Submit order cancellation to external exchange. Submit cancellation request to exchange using external ordered. Cancellation fails via exchange, order failed, exchange down. Respond client fail. Rely on cleanup background process to continually scan pending cancel orders. Cleanup repeatedly queries exchange to confirm true status, ensure eventually canceled, or update status if already filled. 3. Record order cancellation in database. Exchange confirms cancellation. Update internal order status to canceled and order DB. DB update fails. Again, cleanup process resolves pending cancel orders. Ensure canceled or status accurately updated. 4. Respond to client successful. All steps succeed. Respond client success. So, summarize. Clear sequential workflows, coupled with critical idempotent cleanup background process, continually reconciling internal state with external exchange, ensures strong consistency, high fault tolerance, even with various failures. Paramount for financial trading platform. And that concludes our extensive deep dive into Robinhood system design. Many more fascinating aspects to explore later. Handling excess price update bursts, active stocks, further limiting exchange comms, sophisticated batching, how users see orders fill real-time in app, storing, displaying vast historical price portfolio data. But these 3 deep dives illustrate core challenges, robust solutions for scalable, reliable trading platform. #tag outro.
Wow, we've covered some serious ground today. From tracking your personal best on Strava, navigating the complexities of a distributed cache, ensuring lightning-fast local grocery delivery, to the high-stakes, rapid world of Robinhood trades. We've truly peeled back the layers on how these incredibly complex systems are actually built.
Indeed. We've seen the crucial role of clearly defining both functional and non-functional requirements, not just what a system does, but, how well it needs to do it. We explored clever uses of foundational data structures like hash tables, sorted sets, and critically delved deep into challenges of availability, scalability, consistency that turn a basic idea into a truly robust, real-world application.
What really stands out from all this is that system design isn't just picking the right components off a shelf. It's like a dynamic art. It's about understanding the inherent trade-offs in every single decision, anticipating potential failures, and then intelligently building resilient performance systems piece by piece, layer by layer. The solutions often build on fundamental, powerful patterns, but it's their nuanced adaptation to solve specific real-world problems, and that constant balancing act of priorities, that's where it gets really interesting, isn't it?
So the next time you casually track a run, quickly order groceries, or check a stock price on an app, maybe take a moment, consider the intricate dance of data and services happening invisibly behind the scenes. It's that complex choreography ensuring your experience is seamless, fast, reliable.
What other everyday apps do you think hide similarly complex and fascinating system designs beneath their user-friendly surfaces? We're always eager to unpack more.